with the first part being, yeah. So in the previous semester, I believe we discussed link budgeting. Do you guys remember, or should I discuss this in detail? Link budget, guys?
Could you give a like short revision or something?
Yes,
Or
I'll do. I'll spend some 15 minutes, 15 to 20 minutes on this, and I won't go into much details of deriving stuff. So link budget, wait a second, let me, yeah. So basically what you have is that, so one, so let us consider the example of BPSK system. Fine. Fine. This is okay.
yes,
Yes,
sir.
sir.
Yeah. So now let me also consider a wireless channel and power right. Sorry. Fine. Yeah, Bhanu. This is fine. So, but if we transmit with power PT using an isotropic antenna, then PR equals Fine. Fine. Makes sense.
Sir,
Yep.
sir, above EB's energy of
Bit energy or symbol energy.
okay. Sir.
Fine. So so this is fine. Now next step. If the transmit antenna sorry this one has a directive gain GT. You know what is the directive gain of an antenna? Guys?
So you could revise it once. So
Yeah,
please.
okay. So you have done antennas. So have you covered antennas in electromagnetics? That would be the first question, because then I would define this stuff. So have you covered this antenna? Have you covered antennas in electromagnetics?
So it was done in a rush. So I'm
Okay, it was okay. We did cover antennas, but we did not understand. So antenna, or for communication people, antenna is like this point source. This is the transmit antenna that is releasing electromagnetic waves, and this is the receive antenna, which so what the transmit antenna does. Create a time varying EM. Fine. The transmit antenna creates a time varying electromagnetic field. That is understandable.
Okay, sir.
Sorry, Kirti, can you say
yes,
that
sir.
again?
Yes, sir.
Yeah,
Yeah.
fine. So now if the transmit antenna is transmitting at a power PT and is isotropic. You understand what is isotropic?
Sir, no,
I
sir.
believe no.
No, sir.
Yeah. So yeah, an isotropic antenna transmits and receives. So equally from all directions. Fine. So the or the electric, since we are talking only about, I'll only talk only about the electric field. Intensity is uniform across it in space. Fine. This is an isotropic antenna by definition. So the definition makes sense.
Yeah, sir.
Yeah, great. So now this means that if I have an isotropic antenna can be seen as a time varying point charge creating an electric field at a fine. This you agree?
Yes, sir. Yeah.
On a conceptual level, I'm just giving an overview of these things. So now if you have a point source like this, so basically the power, so if it transmits at PT, then the intensity of the electric field or spatial distribution of power that I'll represent as S as a function of D, distance D is fine. It will be evenly distributed on the surface of a sphere with a radius D.
Yes, sir.
So, or let me call this just S. S is PT. Now, at a distance D, if you place an object of area, say AR, then basically what will happen is that a wavefront is emanating from this point source. Fine. And this wavefront that is emanating from this point source will propagate, and this will be intercepting this electric field. Fine. Agreed?
Yes, sir.
So what is the AR? It's a region, that's it.
Yeah, AR is area of the interceptor. So you can say that the sun is a source of electromagnetic radiation, for example, and you place a solar cell outside. So the area of the solar cell will decide how much sunlight it can accumulate, right?
Yeah, so basically like a receiver kind of thing, like this a receiver.
Yeah, so this receiver antenna has an area or aperture AR.
Okay, sir.
Okay, so based on this, the power intercepted by the receive antenna with an area aperture AR is right?
Yes, sir.
Now, practically, what is happening is that we have an antenna here. This we want that it should be receiving. This antenna we want to receive, but all the other directions, we are actually wasting the power. Power is getting wasted, right?
Oh, yes, sir.
Yeah, so practically we want directive antennas or antennas that can radiate in one particular direction. So we practically we want non-isotropic antennas. Fine.
Yes, sir.
And the gain of a non-isotropic antenna is defined as the ratio of the peak power intensity of that antenna divided by and the power intensity of an fine. As an example of an isotropic antenna, consider a street lamp. Will anyone disagree that a street lamp is an antenna? Is a street lamp an antenna?
It emits light, so light could be electromagnetic, so kind of.
Precisely. So a street lamp is an antenna. Fine. So consider a street lamp. Now this is a bad drawing of a street lamp. So let me put some ground here. So this is a street lamp and this is basically the area covered by the street light, right? What it has is that there's a reflector behind there's a bulb here. These days there's an LED and there's a reflector behind, so there's no light going here. There's just everything is being reflected into this region, right?
Yes, sir.
Agreed? So basically what you are doing here is that whatever light would have gone up here, you via this reflector, you are focusing all of that into this region. Or the street lamp is forming a beam downwards. Right? This makes sense?
Yes, sir.
So how many of you have heard that your parents say that if you are placing when there's a power cut, if you are placing a candle next to a wall, instead place it next to a mirror so that more light will be reflected into the room. Do anyone else's parents do that? I'm not talking about horror movies. Oh, okay. Only my mom did that.
Usually there's a you like battery connection which
Sorry?
is already. We don't usually have power. It's the knife
Oh,
map.
yeah, so yes, you guys are from another generation. Yeah. So when I was younger, there used to be power cuts, and my mom used to place the candle next to a mirror so that the there is so the max instead of placing it next to a wall or a non-reflecting surfaces, the surface simply to call not call spirits, simply to allow more reflection of light. So that is introducing directivity, because all the light that falls on the wall is getting wasted. You want to maximize the area. Yeah, I would be scared that it will call ghosts. So I used to remove the candle from there. That's a separate story. Yeah, but so we are trying to focus the beam downwards, and if you get constructive interference, you will get more intensity. So if I draw a point source like this, so see, this is the point source. This can be the origin of a circle. If I talk about an isotropic antenna, an isotropic antenna can be like this, but we would want the strength of the antenna, or we would want the beam of the antenna to be focused in one particular direction, possibly towards the intended receiver. So I would want the antenna beam pattern to look somewhat like right. This is what I would want. Now it has changed colors. You guys agree? In case of a street lamp or in
Yes.
case of a torchlight, when you are
Yes.
wielding a torchlight, you don't want the light to fall back on your face. This. So this is called, so naturally the power here would be more than this. So peak power of the peak power of the directional beam and power of peak power intensity. Power intensity of the isotropic beam. Fine.
Sir,
Yeah.
sir, the like the isotropic wave, this thing you have drawn, right? That is that's a collection of all equal power of like in power intensity curve point, right?
Yeah, that is a circle basically. Or in
So
3 dimension, that would be a sphere.
like the one which you have drawn for the this thing directional beam, like on what, how did you join that curve, like draw that curve, say exactly like how you are
So that is what we want. We ideally want a laser pinpoint. So if you have a point-to-point communication link, you would want that all the power be concentrated at the receiver, right?
yeah, yeah.
Yeah. So for this, how do we do this? You have to possibly look at a textbook on antennas, and there are something called antenna arrays. Did you hear the term antenna arrays?
I didn't.
Yes.
Yes.
Yeah. So there are something called antenna arrays where you have multiple antennas. So for example, this is not the part of this course, but yeah, since this is important, or since as ECE students you should know this, I'll spend some time on this. So suppose you have these point sources, isotropic antennas. Fine. Now this is transmitting some ES. This is ES e to the power j phi. and so on. Now, what you can do here is since these are spatially separate, you agree that these are spatially separate antennas.
Yes.
So now at a particular frequency, say at a frequency FC, if I try to transmit, if I transmit this, so the way at this point, multiple waves will be arriving at this point from these different antennas, right?
Yes, sir.
Yeah, so multiple wave fronts from each of these antennas will be arriving at the destination in an array. So since multiple wave fronts will be arriving at the destination, they could add constructively or they could add destructively.
Yes, both are possible.
Both are possible. So if I can control the phase of the transmitting wave so that they add constructively at the points that I want them to, and they add destructively at the points I don't want them to, it will be controlled interference.
Yes, sir.
So if I change these phi, if I control this phi or phi 1, phi 2, phi 3, phi n, if I control these such that I get constructive interference at the points of my choice and destructive interference at the points of my choice, I can control the pattern of the beam.
Yes, sir.
So the pattern of the beam is basically the pattern of how is the power spatially distributed. Agreed? Kirti? Make sense?
Sir, could you repeat it once again? Like my
Yeah,
internet.
so if I so these all of these wave fronts will reach different points in space. You agree on that?
Yes, sir.
So at all, and all of these can have different initial phases. I can control those initial phases.
Yeah.
So now if I control those initial phases such that wherever I want, these add constructively, and wherever I want, these add destructively, I can control the shape or the spatial footprint of this thing,
Yes, sir.
of the combination of these antennas,
Yeah.
right? This is called beamforming.
Okay. Okay, sir.
Obviously, in a antennas and electromagnetics course, you would spend some 10 to 15 lectures on forming beams or beamforming, but just to give an overview of the idea. So the antenna is no longer, or you can have a non-isotropic antenna from a combination of isotropic antennas, right?
Yeah.
So you can, that way via some manipulation, we can have this kind of a beam, or we can make all the power point to wherever we want it to. We can use a reflector, we can use an antenna array, we can play a lot of tricks. Fine, all those tricks are relegated to an antennas course. One, I do not remember all those tricks. Two, this is not the right course for them.
Fine,
But
sir.
I hope you get the idea.
Yeah. Yes, sir. Okay.
Yeah. So now, since I can get better than an isotropic antenna performance using an antenna, we define, therefore can define what an antenna has to offer over and above an isotropic antenna and call it the gain of that, or the directive gain. The gain, it is called the directive gain, since is fine. Directive gain. Also, it is important to note that an antenna is a passive circuit element. Since we are discussing all of this, and this is one of my favorite interview questions, that an antenna, despite being a passive circuit element, you say that an antenna has a gain. Simply because it doesn't add power to anything. What you are doing is you are redirecting power from one location to another location. So that's why an antenna has gain. Make sense?
Sir, but an antenna can increase the strength of the signal, right? Or it cannot.
Antenna can, so an antenna C is a passive element. That we must be clear. It can only transmit what we give it. There is no additional source of power. An amplifier, for example, has an additional source of power. An amplifier has a DC component that is used to feed it power, and that allows it to increase the signal. An antenna doesn't have a secondary source of power. It's a passive element.
Sir, so is a amplifier often cascaded with an antenna?
That is a separate thing.
Okay.
That is a separate circuit element. So the amplifier is, you define the amplifier gain because it takes power from a DC system and amplifies the AC system. That's why we call it their gain means that what in terms of AC power, whatever you are gaining in terms of AC power. In an antenna, there is no secondary power source. Yet we define the gain of an antenna as the peak power divided by the isotropic power. Fine? Or you get what I'm trying to say?
Yes, sir.
Yeah, excellent. So, and in general, I don't remember the derivation because honestly, I wasn't prepared for the fact that you guys haven't covered this. So I was going to take this for granted that in general, the gain of an antenna with an aperture AR and operating at wavelength lambda is GR equals 4 pi AR lambda square. Fine. Also, since PR equals GT PT
So okay, I have a doubt.
Yeah.
So the gain of the antenna will like depend a lot on the surface on which it is reflecting, right? So when you said 4 pi AR upon lambda square, what kind of surface are you like taking it by default?
By default, metal.
I mean, the shape of the surface will like matter more, no?
Yeah,
Like
I know
to
that.
gain.
I know that. So that's why I said that I'll just consider direct expression. Antenna theory, you can look at Balanis's book. That guy has
Okay.
derived a lot of things.
Okay, sir.
Okay. And there, there are a lot of expressions for antenna gains, and this is the most general expression. Or this is the for communication people. So we communication people like to stop at characterizing the antenna and leave everything to the electromagnetics people. So this is the one of those places where we meddle slightly with electromagnetics. So I have done a course on antenna 11 years ago, but that was the last time I studied antennas. And since I didn't know that you guys have an online antenna semester, or you guys have studied antennas in the online mode, and that part is slightly shaky. I didn't I actually don't have a book for all those derivations, but possibly you guys can go back and look at it somewhere. So all I know is that all these derivations. So the book is called Antenna Theory. This is a beautiful book on this area. You can possibly get your hands on it and try seeing the derivations of these expressions. Fine. But I remember that this is a good book because even 11 years after reading this, I still remember the title of the book and know that this is a good book. So this shouldn't be hard. You can find this book easily. So find this I can write
Yes, sir.
as fine.
Yes.
Now if I tell you that I require of X receiver can calculate the required, right? You can calculate the required dB by N naught.
It's a full form of BER.
Bit error rate. Or symbol error rate. In case of general constellation, since we started with BPSK, fine. I can
Yes,
do
sir.
this. So now if you can calculate the required EB by N naught. Yes. So if you can calculate the required EB by N naught, the next step is
So N naught is
coming to that. So N naught is KT. This we did in the previous semester. Boltzmann constant and temperature.
okay, sir.
Fine. EB EB is right.
Sir, it shouldn't be PR by W.
Oh, yeah, PR by W. My bad. Fine.
Yes, sir.
So can so given GT, GR, D and lambda, I can calculate PT. So I can calculate the transmitted power. Agreed? Or I can tell you, given that this is the configuration, how much power should I transmit so that I am able to achieve a better symbol error rate given by this. Makes sense?
Yes, sir.
Yeah, so this is called, so I can budget. I can therefore budget the transmit signal power. And this is called link thing for analog channels. Another way of looking at this is regenerative repeaters. I transmit this signal. There's a repeater here. There's another repeater here. There's another repeater here. So I transmit this. It gets decoded. It gets decoded again. It gets decoded again. Fine. This is a regenerative repeater. So I split this instead of transmitting it over a long distance. I transmit it over several short distances. That allows me to transmit with smaller powers because that Q function is a nonlinear function, or Q function is a quite fast decaying function. So this you actually have to. So what I would say is that instead of me telling this to you, you can actually go ahead and read out. So this I always tell people to read themselves. read page 437 and 438 of the textbook. Fine. This will cover whatever we want to discuss about regenerative repeaters. So topic number is 7.7. Fine. So we'll be skipping synchronization totally, and the next topic that I wanted to start today was digital modulation with memory. But since we just have 5 more minutes left, 7 more minutes, I won't start with that. What I would instead do is list out all the topics that are left, and then we can decide. So one is Markov chains. Have you guys ever heard of Markov chains?
So I only heard of it.
Sir, our information theory course has some background on it.
Okay, I'll cover Markov chains again in one lecture. Digital modulation with memory. 2 lectures. Demodulating memory signals. 1 lecture. Then you have we have covered this, we have covered this, we have covered this. So we'll cover this later. So yeah, power spectra of modulated signals. Two lectures. Then band limited channel modeling. One lecture. Signaling in band limited channels. Three lectures. Afterwards, yes, this is a part of that. And this is, and yes, then equalization. This is just going to be an intro of equalization. I won't go into the mathematics. One lecture. Then 8 OFDM, 3 lectures. So how much is this? 3, 4, 6, 7, 10, 11, 13. 13. So, and how many lectures do we have left? Guys?
So if we assume 40 lectures,
42 actually.
42.
Yeah, 14 weeks, 42 lectures.
Sir, around 16 lectures.
No, okay, wait. So today is lecture 23. So 16 and 19 lectures. Theoretically, 19 lectures are left.
Sir, we would most likely use the last week for the Viva, right?
No, this time I scheduled the Viva that way. That only one lecture will be lost.
Okay, sir.
Yeah, I took care of that. So, and so we have 18 lectures, out of which we have material for 13, or we have 13 or 14 lectures planned. So I'll see if at all. So this is the necessary stuff. All of this. So after this, people have different approaches. They do error control coding, but error control coding, I don't think we have enough time left for error control coding. So there is error control coding, there is introduction to wireless, and there are a lot of other things. So let's see how far or whatever we can do in the time that in the how many lectures we'll have left. So 13 and 5 lectures. 5 lectures aren't good enough for anything actually, or aren't good enough for starting anything new. We'll see what we can do. Okay then, guys. Bye. Have a nice day.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.